Welcome everyone. Good morning, good evening, and good afternoon, wherever you are. My name is Hadi Amal. I am the director for the Digital Advancement Academies in the Americas. I'll try to raise my voice just to make sure that the audience in Houston can hear me loud and clear. The Academy's main mission is really to partner with industry and to be a place for knowledge exchange and best practice. And as part of this, we really welcome you to the first session for the Structural Engineer STAAD Connection Edition. This is both a virtual session where we have tens of people joining us across the world. We will have different we will have different people attending from across the globe, as well as some audience that is present in our Houston Digital Advancement Academy hub. By that, I would like to actually introduce Rail and let him introduce himself and take it forward from there. Thank you.
All right, excellent. Thank you, Hadi. As he said, I'm Rail Karp. I'm Vice President of the Design Engineering Analysis Group. I have the honor to run our product development really for all the analysis products or analysis related products at Bentley. So STAAD, RAM, AutoPipe, SACS, anything that has finite element in it is part of my purview. And recently also the addition of our Plaxis Geotech analysis products is part of my group. So I practiced structural engineering for several years, been at Bentley for over 20 years now, and still excited and enjoy what I do every day. It's really a pleasure to be able to kick things off today. Particularly appreciate again all of those who made the trip to join us in person in Houston, and a quick shout out to any of my Houston alma mater from Rice Owls in the audience, and of course to the many that are joining virtually as well. As I present today here from the NCSEA conference in California, I certainly know that you're very busy. You have choices where you spend your time. So I thank you for flying with us today. So today's all about the STAAD.Pro Connect Edition. I truly believe this is the most significant generational release for us in probably the last decade. You're going to see a little bit later, how this release is really in large part in response to the feedback we received from our users, many of which are with us today. And at the same time, you shared with us, what we should be doing better instead. You also shared with us some of the big challenges your businesses are facing. And it's on that front that I'd like to spend the first few minutes here to discuss and share with you what are we doing to help you with those particular challenges. Okay, so we didn't hear that you wanted more cake to be successful, certainly, but we did hear how your projects are getting larger with more distributed stakeholders and more coordination and interoperability challenges. There's definitely a need for better, more robust collaboration tools. I think the ability to automate your typical work processes was another common theme we hear from our users. We also often hear about the challenges of getting new and experienced users productive on new products and new capabilities. Are you attending the session, no doubt? And lastly, an issue keeping our users up at night is really how to deal with and manage the risk and maintain safety and quality of your designs at the same time as your schedules are getting so compressed. These are some of the top challenges we hear from our users and ones that we're going to be investing and have been investing heavily in. And I'd like to share with you now some of the innovations in these areas that we have been working on. So projects are in general getting larger. They require more interaction, more stakeholders, but also more products in your design process. We actually did an internal survey here a number of years ago that showed on average 5 different structural products are normally used in a single design project. In fact, Bentley has had a similar challenge with the myriad of structural companies and products that we've acquired over the last decade. And it's really why we have been investing really for most of that time in our integrated structural modeling technology that enables all of the products that you see here on the screen to interoperate and communicate with each other. ISM, as we call it, is technology that allows you to control what information is shared between these products, keeps track of who made what changes when. And I'm excited to share with you today that we have recently integrated and are in the process of finalizing this capability, this technology with our new digital cloud, digital twin capability that really enables easy cloud sharing visualization of your common model. But most importantly, it enables better collaboration among stakeholders in a project. Let's take a look at that forms. I think whether you're a structural engineer working with an architect on a project, or a structural engineer working with, say, a pipe stress engineer on a project, as we see in this case, the iTwin Design Review Cloud Service is going to allow you to instantly share your design model with any other stakeholders in the project and conduct a real-time discussion through the web. So from STAAD, you will soon be able to, for example, initiate a sharing session here, combine the structural model with other disciplines like piping, and have a conversation in the cloud with the pipe stress engineer, the owner, or even other structural design partners. In this case, we're going to try and resolve a clash or have a discussion about an issue with a clash on piping and structure, for example. The great thing about this technology is any stakeholder can access this with really just an email invitation. And the even better part of this technology is that they don't need to have any underlying skill set in the publishing product. So no STAAD knowledge is needed in order to utilize this capability. Great way to have an instant conversation in the concept of your project, and that can be documented, tracked, and managed as action items through the rest of your project development. I think another always hot topic for us is automation. Although when we talk to our users, they don't generally use that word. I think we hear more about how they want to be able to enter data once. You want to be able to share it between your products. And most importantly, you want to be able to automate as much as possible, I think, the repetitive workflow needs that you have. For years, probably the biggest improvements in automation have been in the area of design code implementation and automation, and document automation. And really, we've made a fantastic, another major step forward in the STAAD Connect edition that you're going to hear about a little bit later. But more and more, I'm also hearing that our users want to be able to do things beyond what the product can do. They want to be able to extract results, or even automate a workflow of their own, giving them perhaps a competitive advantage in a certain field. But to do either of these things requires a programming interface, and that's another area that we have invested heavily and continue to invest in. And this opens up some very interesting possibilities for you as our users. So by exposing these interfaces, your company can, for example, now string together different products in an iterative workflow. We know, for example, that foundation displacement is a function of the soil stiffness. It's also a function of the foundation geometry and the reactions on that soil. And the reaction are, again, a function of the soil stiffness. So it's highly interdependent design process using different products across different engineering domains. So what if you were able to automatically iterate between, say, the structural analysis and the geotech analysis to produce a more accurate, efficient, combined analysis here together? So now you can, using the programmer's interface between these two products, we can now couple and show an example here of using those programs interface to couple Plaxis, our new geotech acquisition, with STAAD to automate that process. And you can use it for any of the workflows that you would like to within your organization. So knowledge, technology, engineering requirements, they continue to grow, they continue to change. I frankly don't know how you stay on top of the industry and what you need to know, and even have confidence in how you know to have confidence in the source of the information that you're relying on. We know YouTube is one of the largest search engines in the world, great source of information. I highly recommend you subscribe to our Bentley structural channel. But what if you could take it to the next level? What if you could have access and be able to search our officially developed and sanctioned training material, webinar material, help documentation, and yes, even the YouTube clips, all from an easy single access point? With the Connect edition, You now have access to all of that, and even more, frankly, with our new Connect Advisor technology. This is a product that sits side by side with STAAD, and it can easily be called on when needed to do your queries, and it will search again across all of those sources and reference material. In my opinion, the best place to start your search for answers and for expert help, sanctioned by Bentley. We spoke a little bit about automation, how it could make you more productive, but also how our users really have expressed concern and how quality assurance control has really become more critical, a bigger challenge with the pace of design demanded today. Today, the QA/QC process in most firms is a fairly manual process, sometimes validation of some design calcs, spot checks. Very often, it's just a review of the issued construction documents to ensure, again, through a spot check approach, that we have met the QA/QC requirements. In no way is this comprehensive, and it's not very easy to scale and adapt to your increasing demands on schedule. So imagine a world where some of your own quality assurance requirements could be, checks and requirements could be automated. What if you could take the digital twin we spoke about a little bit earlier, and you could, again, write your own rules, your quality assurance rules, and have them automatically run against your design to check that and validate it. Perhaps you want to make sure that all the beams over a certain length have a camber specified, or you have an internal length over depth ratio you want to have enforced. With this new service, the cloud validation service, you're going to be able to do all of that. You're going to be able to establish a list of rules of your own, as we see here. You can then make and automate validation of these custom rules against the model. So the interactive web visualization you see here gives you clear feedback where you have met or failed or exceeded your internal QA criteria. This is a really powerful, easy to use and effective way to automate a large part of your quality assurance, even if it just highlights and identifies areas where you need to focus on for closer review. So I mentioned at the start, STAAD Connect Edition. So it's in large part a response to all of these areas and your feedback, areas that we could do better. I think you will see how, for example, the physical model approach allows much improved interoperability, including now with surface members, faster analysis for bigger projects, concrete design and drawing automation has been taken really to a whole new level with this Connect Edition. And coming soon, the integration with the iTwin services I just showed you is going to be able to deliver many of the digital twin design review and validation capabilities that I just shared. This really, really is our most significant release in ages. So before I hand you back to Sai for what you all came here for, the meat of today's workshop, I did want to extend a huge thank you to really all of you for the work you do, the support of our products and our services here at Bentley. It really does truly motivate and inspire all of us. I'm just back from our annual Year in Infrastructure conference. This is held in Singapore, or was held in Singapore this year. This is an event where we celebrate all of your great work using our products. Yeah, we see this year's structural category finalist and winner from WSP on an amazing project to add and expand the historic Admiralty Arch in London. You can see this presentation as well as all of the finalists just by Googling Year in Infrastructure 2019 and finalists, and you'll see all the 3 finalists presentations in this category. So most importantly, I want to invite and encourage all of you here to submit your projects for consideration to attend our conference next year around this time, which will be held in Vancouver. It's a fantastic event. The awards and the presentation is just a small part of it, but an important part. And really, it's just a reward and recognition for your contributions. So with that, I want to again thank you for your time today. I'm going to turn you back to Sai in our Houston Academy. to share our advancements in the latest and greatest STAAD.Pro Connect Edition. Thank you.
Thank you, Ram. It has been raining in Houston since morning, so it's a rather gloomy day, but you get a great start and brightened up the presentation, so thanks for that. And thanks everyone for joining in live today. And also thanks to everyone who are joining through the web. So as excited as we are with the STAAD Connect Edition, I'm sure this workshop is going to get you excited as well with the STAAD Connect Edition. So this slide, I have tried to list all of the capabilities that we have added very recently to the STAAD.Pro Connect Edition. First of all is the state-of-the-art customizable interface. We have improved the way in which you can work with files on a network drive, because we understand that some of the companies do require you to have your STAAD models located on a network. We have introduced a new system of backup by creation of restore points. I'll talk in detail about that. We added a Chinese steel database to the Connect Edition. There's a STAAD.Pro physical modeler that we created, which is a parallel modeling interface to the analytical that we have. And with every release of STAAD.Pro, we are adding new options to it. It's still under development, but we are adding options at every release. And I'm going to talk about the significant loading options that we added in the Connect Edition for the physical modeler. We also added an edit surface mode, which would allow you to isolate a surface from a complex model and do some local edits on it. We added the IBC 2018 ASC 716 code, so you'll be able to do a static or a response spectrum analysis based on that. You can carry out seismic irregularity checks as per the ASC 7, and those can be reported as part of the analysis output file. We have the integration with RAM connection version 13.1, and I'll show you as part of the presentation how that integration works. Viewing multiple sets of design results, this is something that we have been asking for a long time. Viewing multiple sets of results using the graphic user interface. Because earlier, if you had like multiple design sets, you could only see it in the analysis output file. Only the last one would basically show up in the GUI. But now you'll be able to see all of these as part of the graphic user interface. We revamped our results along cut line feature. And we added the advanced concrete design, using which you would be able to not only do design of concrete beams, columns, slabs, walls, etc., but you would also be able to generate like drawings, bill of materials, and we also have got an extensive session today on that. And then we had a lot of improvements made to the analysis engine. So you will see the improvement in analysis speed, especially for big models. And the interoperability, which Rail was talking about, that's something which has been very big for us. And we are continuously working on that so that you can use your data from STAAD and take it to other packages and vice versa. So I'm going to start off with the first option, which is the ribbon menu. And at this point, let me just quickly go into the software to basically give an idea of the interface. So this is basically the new interface of the Connect Edition. So it's mainly a workflow-based layout where you'll be able to see your entire workflow if you look at this section. So you start with geometry, then you go to the properties, then you go to materials, specifications, then supports, then you define your loading, to the analysis, and then to the design. So basically your entire workflow is up here. So it's a workflow-based layout, and we have this ribbon menu at the top where we have created the interface in such a way that depending on the particular ribbon menu you are in, you will be presented with a selected few icons which are relevant for you. So basically, like if you're in the geometry ribbon menu, you only get to see the geometry creation tools. If you are in the say view ribbon menu, you are only presented with the view related icons instead of having to deal with say 1,000 icons. And then you have the various modes, like the analytical modeling mode, physical modeling mode, the post-processing, foundation design, the connection design, all are along the left-hand side of the interface. So one change that has happened is these options used to be up here, immediately above the graphics, if you were migrating from V8i. And the options, the workflow options that I spoke to you about, this used to be on the left-hand side, but it wasn't arranged very logically. So this one we felt would be much more clearer and would give you a better indication of what your workflow should be. Another thing that I would like to highlight, especially for the users who are migrating from V8i, if you look at this right-hand data input area, you will find that this looks exactly the same way as it used to be in V8i. For example, if you go to properties, you see the properties whole structure window. If you go to specifications, you see the exact same window. You go to loading, again, the same window. So if you are migrating to the Connect edition from V8i and struggling initially to find the various icons, this is one thing that would help you, because you can continue to work using the right-hand side, the data input area on the right-hand side. And that way, there'll be minimum like disruption to your workflow. But while you do that, I would also encourage you to take a look at these ribbon menu options, because once you get familiar with this, it's really a joy to work with. So definitely something to check out. And the other beautiful thing about this new interface is it is customizable to a large extent, in the sense that if you use some icons more than the others, then you can actually have these icons displayed in here continuously at the top. So these type of customizations are available. So to do that, you can just simply come here and choose the Customize Quick Access toolbar and choose More Commands, and it will give you access to all of the icons or all of the commands that STAAD.Pro supports. And every command is available here. If you want the commands to be grouped, you can just do that. So I'm just filtering based on the utilities. And let's say you use the unit converter a lot. So I would, let's say, include that. Let's say I also take pictures of my model quite often. So I can include that. And whatever you need to include, you can do that. And once you click on OK, these icons are going to show up continuously at the top. So these are customizations that you can always do. If you think that this is occupying too much real estate in your laptop or desktop, what you can also do is there's a quick commands menu that you can just access by pressing the space bar on your laptop, and it gives you access to the quick commands, and it works exactly the same way. So you can just go here and just select whatever you need to select. So let's say I choose the command file for the input editor, and let's say the cut section option. And now if I just press the spacebar once again, you see these two options would show up here. So whatever you need to use, you can just customize, either include it in your quick commands or include it as part of the menu at the top. Okay, so let's go to the next slide. And I have actually created this slide in order to just highlight the fact that these customizations are saved in some XML files. And we have got a wiki created in Bentley communities. And we are going to share this link with you so that you have access to this information. And so these are the 3 files which you need to copy. And when you have a new installation of STAAD.Pro, you need to replace the same files with these files so that any customization that you have made are retained. I was talking about some improvements that we made for working with files on a network. So let me quickly show you. In a model, now what you can do is, if I just close the model for a second and go to the configure option from the startup page, you can go to options, and now you can set a temporary location in your local drive where STAAD.Pro can copy your model during the analysis. So this is certainly going to help with the performance of the software and will give you a faster analysis. But having said that, I would still recommend that if possible, just keep the model on your local drive when you're working with STAAD.Pro. And once you are done, then you back it up on your network server. But if that's not possible for you, then the next best option would be to use this option. So designate a temporary folder in your local machine so that the model can be copied during the analysis. Okay, so going back to our next slide, we actually introduced a new system of taking backups, and now you can actually create restore points. So say, for example, you are making major changes to your model and you would like to keep copies of those. Earlier, you had to just save the STAAD model by different names. So there used to be like multiple STAAD profiles for the same project, but you don't need to do that anymore. You can just create restore points and add adequate descriptions to these restore point backups. To do that, let me just open that same file, and you go to File, and then here is the Backup and Restore option. If I go here, you can see that a number of restore points have already been created for the same model. So, and there are some descriptions which are attached to each of these restore points. Say, for example, the braces have been assigned as trusses in this version of the model. Here, the braces have been assigned a particular type of angle section. So you can create as many restore points as you want, and that would allow you the ability to just restore any version of your model. And to create it, it's pretty simple. Just click on the create restore point. It would automatically give you a name. Just put your own name, add your own description in here, and if the model is already analyzed, you can use the checkbox include analysis data, and then click on create, and it will create a restore point for you. And to access it, just go to the restore model. And so this is the last one that we created. And any of these previous versions can be restored by using this icon on the right. We added the Chinese STI database GBT 706 2016 for those of you who are doing projects overseas and use Chinese sections. You will find it useful. The next thing I'm going to talk about is the physical modeler. As I mentioned, this is a new modeler that we had created with the Connect edition, and that allows you to model members physically. So, and we added a bunch of new loading options, starting from snow load, wind load, temperature load, variable pressure load on the surfaces, hydrostatic loads, the ability to add inclined loads, and then to do repeat loads. So I'm going to just quickly go to the STAAD.Pro model, and let me open up a physical model and talk a bit about the physical modeler. So here you can see that there's a physical option in here. This is the analytical. Right next to it, there's a physical option. And I have a model created in here. Just open that up. So this is the physical modeling interface, which is again ribbon menu based. And the reason we call it physical is because, say, if I zoom in here and if you look at this beam member, so this is basically modeled as one single member. But if you are doing the analytical model, you already know that you need to split this beam into multiple segments so that connectivity can be established with the members which are orthogonal. But in this case, since it's a physical model, you can actually continue to model it as a single beam. And same for these walls at the base. So these are modeled as one single surface. This foundation at the base is modeled as one single surface. So internally, when the software is going to generate the analytical model, it's going to decompose this physical model into its analytical components. And in the process, it's going to maintain the connectivity between the various entities in the model. So talking Talking about the new additions that we made. So we added the wind load definition in here. So now we would be able to define intensity versus height data for the wind. The load generation as per the codes like ASC hasn't come as yet, but we'll be including that too in the future versions. But right now you can generate your own wind intensity versus height data. And similarly, you can define your snow load up here. And if I just go here, I have already defined a couple of loads for you. If I go, select a temperature load, let me view the model from the front and select these beams at the top. So you will see that I have applied temperature load to all of these members. So whenever a member is selected, then if you go to the member menu option, ribbon menu option, it will give you the options which are relevant for the members. And then you will see the temperature load in here, where you can specify the delta T basically for axial elongation or for difference in temperature between the top and the bottom of the beam or between the sides of the beam. Similarly, there are a number of options that have been added for the surfaces. So if I just select a surface, if I go here, you will see an option to add a variable pressure. So at various points on the surface, you can specify a value of pressure. That is possible. We also, so if you want to see how it looks like, I have created a variable pressure load in here. So you see that there is a trapezoidal pressure distribution that I have created using this feature. Similarly, you can add a hydrostatic load. So there's a trapezoidal hydrostatic load that has been added to the inside of the wall. And for hydrostatic load, all you have to do is basically just select a surface, go here, and just use this option, hydrostatic. And then you'd be able to define the density of the fluid that is retained and the level at which the pressure is zero. So basically, that's how you specify the hydrostatic load. And then let's say, for example, you want to define some inclined loads at the various nodes. So all you need to do is just select the node. And then if you go here, node, there's an option called nodal load. And that would allow you to define an inclined load parallel to any axis. So basically, you define a local axis, which can be at any inclination to the global axis, and then your loads can be defined with respect to that. So I just choose that inclined nodal load option, you will see that a number of loads in inclined directions have been applied. And this is with respect to this local axis. As you can see, it's inclined to the local to the global axis system. And if you are trying to define repeat loads, all you have to do is go to File, Options, and then within the analysis model, you're going to see the option to generate the repeat primary load cases. So these are new loading options that have been introduced in the physical modeler. Going back to the next slide, this is the new edit surface mode. So basically, you can select a surface and do some edits locally. So for example, if I just go back to my model, now before I make any edit to the surface, let me show you how the physical model is converted to the analytical model. So for that, you would have to just choose Return to Analytical Modeling option on the right-hand side. So at this point of time, the software is going to break up all your physical members or physical entities into analytical segments and get the model ready for the analysis. So once it's completed, you can click OK, and it's going to give you your finite element model. As you can see, all of these entities are now meshed properly. There is proper connectivity maintained between the bottom slab and the walls, although we just defined the bottom slab and the walls as just one surface in the physical modeler. Similarly, these beams, which were just specified as single members, have been broken up into segments so that connectivity is established. So let's say I want to create an opening on one of these walls. So I just wanted to show you, look, how easy it is to use the physical modeler for these sort of purposes. So I'll go back to the physical model, and let's say I'll select this surface. And if I go to surface, there's an option called edit surface. So from this model, that particular surface is going to be isolated, and I'll be able to work locally on that particular surface. And let's say I want to add an opening to it. So I'll go to circular opening, I'll specify the radius, and then click on OK. And there's a grid already that's created, and you can control the settings for the grid. And you just come in and select the center of that circle, and it creates the opening for you. And then it's not part of your main model as yet, but you can go back to the edit surface, and at that point of time, it will ask you, do you want to commit this change and make it a part of the model? If I choose yes, then it will basically create that opening in here. And if I then go back to the analytical model, so it's asking, do you want to save the change? I'm choosing yes. So basically, it's going to bring the change to the analytical model, and it would readjust the mesh. But if you want to do the same thing using the analytical modeler, you'd need to actually get rid of the mesh for that particular wall, and then recreate that wall with the opening. So if I just view it from the front, and let's say I select the plates which are for the wall, and go back to this view. Now you can see like how that opening has been created in that. So these are kind of flexibilities that the physical modeler allows you. And as I said, it's something that is under development. We are working on it, and so with every version, we are adding new capabilities. But if you are someone who enjoy modeling with physical entities, this is the right time to get your feet wet and start experimenting with it. We added the IBC 2018 AC 716 code, so you'll be able to add this code. Will be available as a selection for you. And when I go into the steel design portion, I'll discuss about this one too. Now, STAAD.Pro has the ability to carry out some irregularity checks as per the ASCE. So you'll be able to check the torsional irregularity, extreme torsional irregularity, and make the geometry checks, like say reentrant corners, or you'll be able to check if there is an uneven distribution of mass at the various heights of your structure. And at the end of it, in the analysis output file, you're going to get a report like this, where it will show you the various checks. And on the left, I have included the commands that are required for this feature. We introduced the connection design using the RAM connection version 13.1. I'll do a little presentation on that down the line. And the highlight of that one is the addition of the New Zealand code to the RAM connection interface. Viewing multiple sets of design results for the AISA 36016 code, this is something which as a user, I'm pretty sure you'll be all excited about. Let me just show it to you. So I go back to the analytical model, go back to the steel model, and if you go to the post-processing, then here you will see the various parameters. So each of these represent a particular code check done with a certain set of input parameters. And now you'll be able to see all of these using the graphic user interface. So if I turn off the displacement and turn on the utilization ratios, and now, so this is for the parameter 1. If I change to parameter 2, it will just update my view to the parameter 2. And similarly, you can get those shown in your design tables as well. We actually revamped the results along cut line feature. So now you're going to have like stress continuities across element boundaries, and equilibrium of forces will also be maintained along the line. So the results that you are going to get using this feature now is going to be much better than what it used to be. The advanced concrete design, we have a detailed presentation on that later on, using which you'll be able to generate detailed drawings and bill of materials, etc., straight off your STAAD.Pro model. We made significant changes to the analysis engine, so you are definitely going to experience a lot better performance from STAAD.Pro. Even if you are using like a STAAD.Pro standard license, and if you are using V8i and V8i versus Connect Edition, like you would see a 1.5 times improvement in performance. So a standard license used in V8i compared to when compared to a standard STAAD.Pro license in the Connect Edition, if you compare it, the Connect Edition one is like 1.5 times faster. Of course, it varies from model to model, but the difference is more significant when you have like more complex models that takes like a long time to. These are models where you are really going to see the performance improvements. And then again, even in the Connect Edition, if you are using the basic versus the advanced license, advanced is a lot faster. And Rail talked about the interoperability at the beginning of the presentation. I've also included this specifically to highlight a few of those. Like we have got direct integration with STAAD Foundation Advanced, using which you can do the foundation design straight off your STAAD.Pro model. I'm going to show you that. The RAM connection integration, again, I'm going to show that to you, how you can quickly generate connections, connection calculations and drawings from your STAAD.Pro model. Then we have the advanced concrete design, or the RCDC. That's going to allow you to generate drawings and bill of materials from within STAAD.Pro. And last but not the least, the auto pipe integration. So you'll be able to bring in any piping loads into your structural model, and then send back the combined piping and structural model back to AutoPipe for further analysis. And apart from the direct integration, we also have the ISM-enabled integration. So any package that is ISM-enabled would be able to communicate with STAAD.Pro, be it a Bentley software or a third-party software. So all of our RAM-suited products, and then Pro structures, and all of the Bentley products which are ISM-enabled can now talk to STAAD.Pro. And also the third-party products like Tekla or Revit, you can also get data from those packages. So at this point, I'm just going to go into some analysis and design and show you how it is done in the STAAD.Pro Connect Edition. And I'm going to specifically focus on the direct analysis, because that is the latest analysis method and the most widely accepted analysis method recommended by AISC. So as you know, it basically allows you to do both ASD and LRWT method of analysis and design. Both are permitted, but the code recommends that if you are doing an ASD method of analysis, you need to multiply your loads by a factor of 1.6. The idea is to analyze your structure for the strength level loads. And then once the analysis is done, you divide the results by 1.6, and then you do the further processing, like checking the serviceability or checking the strength. For the LRWT method, there is no such requirement. You just analyze for the LRWT combinations, and you analyze and then design as per the LRWT method. So both are implemented in STAAD.Pro. The code recommends that you include the large delta and the small delta effects as part of the analysis. And any structural imperfections also needs to be accounted for using the notional loads. Notional loads, as you all know, is a certain percentage, like 0.2% or a 0.3% of your vertical load that you need to apply in the lateral direction, and in both directions, both orthogonal directions. So these are things which you can do when you carry out a direct analysis in STAAD.Pro. And last but not the least, it also allows you to account for the stiffness reduction, axial stiffness reduction and flexural stiffness reduction of the members. So we'll see all of this. Let me bring up the STAAD.Pro model back. And actually, let me just show you a 3D rendered view of the structure. I haven't really spoken about the structure as yet. So it's a typical industrial structure, as you can make out. It has got multiple levels and braces in the vertical as well as horizontal planes. And I've got a few projections on the sides The platforms have a little projections. These are supported by knee braces. And at the bottom, I've included a few concrete members. So at the grade level, you see a few concrete beams supported on a few concrete columns. So we are actually going to do an analysis of this structure. So I've specified all of these specifications that you'll be able to check out later when you get the model. Like this will be, so all of the braces have been specified as like trusses, as specified a number of releases at the various beams. And then the loading, what I have done is I've included the IBC 2018 seismic load generation. So this is something that has been added in this version, IBC 2018 AC 716. All the parameters have been specified relevant to the code, and some seismic weight has been added as part of the seismic definition. Then I've done the direct analysis definition, where I've specified the flex parameter. So flex is basically, if you remember, the code asks you to make modifications to your flexural stiffness, and there is a tau b that tau b term in that flexural reduction. So what you are specifying here is the initial value of tau b for the first iteration. So that is specified as 1. So basically, it's like 0.8 times tau b times e times I. So for the first iteration, you're specifying the tau as 1, and for the next iteration, the software is going to figure out the axial forces in the members, and it's going to calculate the value of tau. Now, initially, when the direct analysis came out, we were supposed to assign these flexural stiffness reduction to only the members whose flexural stiffness would contribute towards the lateral stability, lateral stiffness of the structure. But then the code also mentioned in the later versions that it's better to assign it to the entire model so that you have a uniform stiffness distribution. Because if you assign it selectively, there's a chance that you're going to jack up the stiffness or jack down the stiffness at different locations, which may interfere with your force distribution. So that's the reason I've just assigned it to every member. FYLD again is the yield stress used for the calculation of the tau b. And then you have the axial parameter. This is for the axial stiffness reduction. That also has been assigned to the entire model. So basically, there's 2 parts. There are 2 parts to specifying the direct analysis. You do the definition in here, and then you include the analysis command. Now, if I go to the load cases, I have added the seismic load in X direction, seismic load in Z direction from the IBC 2018. Now, this is a long-standing requirement in STAAD.Pro that if you are using seismic cases, those has to be the first cases in your model ahead of any other load case. So these are defined ahead of your dead load case, ahead of your live load case. And each seismic analysis command would have to be followed by a perform analysis and change. So that is also a long-standing requirement. I'll show that to you when I go into the input editor. And then I have defined a number of combinations from 101 to 114. As you can make out, these combinations are basically the serviceability checks. So for serviceability checks, you don't really need to carry out direct analysis. Direct analysis is mainly intended for your strength design. So that is why I have created this model in such a way so that I can explain both this to you. So what I've done is for the load cases 101 to 114, I have just analyzed using a simple iterative P delta, a second order analysis. No stiffness reduction, no notional loads, nothing. So your full structural stiffness, and then from 201 to 216, these are the actual factored load cases. And these are cases which are going to be used for strength design, and I have used direct analysis for that. So the stiffness reduction, addition of notional loads, everything has been done for these cases. So if I just go to go to my input editor for a second. First is load 1, which is the IBC load applied in the X direction. IBC load applied in the Z direction, each followed by a perform analysis and a change, if you note it. This is important because when you are running a file with multiple analysis commands, you need to ensure that you use perform analysis and change after every analysis that you do. So the change basically resets your stiffness matrix so that it is ready for your next set of analysis. So if I go back to 114, after that I have included a p delta 15 analysis small delta command. So 15 just is the number of iterations. Usually 15 to 25 iterations are good enough for your model, because if you change this value, then you'll be able to see, like after a certain number of iterations, there'll be no more difference in your results. So usually 15 to 25 should be fine, followed by a change command. And then you have the load cases 201 to 216, followed by the direct analysis. So this basically ensures that your strength cases from 201 to 216 are analyzed using the direct analysis. And after that, I have now, although I'm showing you these commands in the editor, but you can as well specify it using the graphic user interface. So you go to analysis and design, analysis commands, and there you have the direct analysis command in here. Or if you are doing the p delta, that also is in there. The perform analysis, p delta analysis, everything is in there. So once you set up your loads, the next thing you need to do is set up the envelope. An envelope is required for the design phase of it. So you need two envelopes. One is the serviceability envelope, another is the strength envelope. So so here, if I just bring up this dialog box, you will see that 101 to 114 has been flagged as serviceability, and then 201 to 216 has been flagged as like strength envelope. So the reason we do that is when you ask the software to do a steel design as per the AISC 360 code, it will automatically do serviceability checks on those load cases which are part of the serviceability envelope, and it would do the strength checks for those cases which are part of the strength envelope. So that's automatically done. But it's important that you have these envelopes defined. And one more thing you have to do is before you start putting in your design command, there is a load list command that you need to include. There's a load list env. Env is abbreviation for envelope, followed by the envelope numbers 1 and 2. This is something that you should always include before doing the code check. Now, unfortunately, there is no option in the GUI as of now. So for now, I would suggest that you just use the editor for this one, but we are going to add this in the GUI down the line. So once that is done, then you go and specify your code check. So as far as tree design is concerned, these are the various checks that are carried out. So it starts with a slenderness check. If it's a member subjected to compression, it checks against an allowable upper limit of 200. If it's a member subjected to tension, we check it against an upper limit of 300. Then the software checks for axial tension, axial compression, shear, flexure, torsion, and also interaction of like the flexure, tension, compression, shear, and torsion, if appropriate. And then it does a deflection check also. So we're going to take a look at these checks. One thing that I wanted to highlight is in the AISC 36016 implementation, there is one thing that is different in our implementation in STAAD.Pro, which is the sign convention that is used for reporting. So if you remember, in STAAD.Pro, x-axis is the longitudinal axis, whereas z-axis is considered as a major axis, and y-axis is the minor axis. But as per AISC convention, x-axis is considered as a major axis, and z-axis is basically the longitudinal axis. So while reporting the AISC 36016 design, we are reporting it in terms of the AISC specifications. That is one deviation from what we have done in the past. And this is actually explained pretty well in our analysis output file. Let's go and take a look at it. So before I dive into the design part, let me just show you a couple of important parameters that you need to be mindful about. So basically, first is you select the current code, which is the AISC 36016. So after you go to design, you select the AISC 36016, or if you want to design as per any of the other older versions of the code, those are also available here. And I've specified a few parameters which I think you should pay attention to. One is the method. So depending on what kind of loading you have used and what analysis method you have used, you would choose the design method as LRFD or ASD. So we used the LRFD approach of analysis. So we are choosing the method as LRFD. Then the FYLD, which is for the yield stress. So I have specified 50 KSI for like majority of the members and 36 KSI for a few braces. And then the DFF is basically for deflection check. If you want STAAD.Pro to do a deflection check, you would have to specify the DFF parameter, because otherwise it won't do any deflection check. So the two criteria that needs to be satisfied is you have to have the serviceability envelope defined, and you also need to have the DFF defined. And then these are the ultimate tensile strength of steel. So FYLD and FU, these are the assignments of parameters that you need to do to the appropriate members. And then there are a couple of other important parameters, like say LY. Now this is used for specifying the unsupported length of the member. So for example, in this case, if I just highlight this, and if I show you a 3D rendered view of this digital connection, so you have the white flange, and then it is supported by the chevron brace underneath. So as far as the major axis bending of this member is concerned, you already have the braces modeled. So it is split at the center. So you don't need to specifically go in and specify any unsupported length when it comes to bending among the major axis. Whereas if you consider the bending among the minor axis, the entire length of the physical member needs to be defined as unsupported. Now, unless you specifically go in and define that through the LY parameter, the software is just going to go with the default member length or member length of the analytical segment. So just be mindful of these things. So that's the reason I have specified LY as the 22.33 feet, which is the entire distance from this column to this column. Whereas I have not specified any LZ, because by default it will be taken as the length of the analytical segment, which is fine. Similarly, you would also have to specify the UNT and the UNB, which are for like laterally unbraced length of your compression flanges. These are used for your lateral torsional buckling checks. So UNT and UNB needs to be specified. UNT stands for the top flange, and UNB, the unsupported length for the bottom flange. So you specify that. And I have also specified one more design parameter at a different location in my model, just to highlight the difference. So for this particular member, in fact, what I can do is I can view it from the, let's say, the front view, and just isolate these members. And let me do a rendering. So basically, for this particular member, this main beam, as you can see, as far as bending about the minor axis is concerned, it is braced by the members in the orthogonal direction. So in this case, you don't need to specify any LY, but you need to specify LZ, which is for the major axis bending. So that's the reason I've done here. Similarly, for the deflection check for this member, if I turn on the node numbers for a second, let me turn the view a little so that you can see it, and let me turn the node numbers on. So if you see the node number 50 and node number 49, these are the two end nodes as far as this entire member is concerned. So that's the reason I specified DJ1 and DJ2 as 50 and 49 respectively, so that when it calculates the deflection, it considers this entire length between the DJ1 and DJ2 as the unsupported length of the member. So just be careful about specifying the design parameters. So simply selecting the design code and choosing the design command doesn't really give you a correct design under all scenarios. So just be mindful of that. So once you specify the design parameters, then I have used the check code command, which basically checks the sections that you have selected. and it tells you whether it's appropriate for your loading conditions or not. And at this point, I'm just going to go into an analysis output file, and I'll just walk you through the output of the AISC 36016, since it's a bit different from what we have done in the past. So I have just selected a member here, and here is where it actually details the sign convention that I was talking about. So the AISC 36016 conventions are clearly laid out here, and along with the STAAD sign convention, so that you are aware of it. And then it goes into the detail of the design. So first of all, it tells you that the code is the AISC 36016 LRFD, and then the member number, what profile it is, so white flange, which database it is coming from, then whether it's a pass or a fail. Then it gives you the ratio, the most critical ratio out of all of the limit states that it's checking for strength, and also out of the serviceability. This is the load case, which is the most critical. Then it gives you the location from the start of the member. So at 11.16 feet from the start of the member, you have this critical section for design. Then it also gives you the clause number from the code, which is critical. And then these are the forces in the critical section. And then it checks for slenderness. Since the member is in compression, as indicated by the C out here, it checks for slenderness against an upper limit of 200, and the member slenderness is 176. So we are good out here. Then it moves on to the strength checks. And so for serviceability and strength, you get the two different ratios. So this is the serviceability highest ratio in terms of serviceability. This is the highest one in terms of strength. So higher of the two basically governs your total design. So that's the one which is reported up here. And then it reports a few section properties, material properties, and then it does a section classification. So it separately classifies the section for flexure and for compression. And it gives you classification for the web and the flanges. And so it uses the appropriate classification when it does the corresponding check. Then it goes on to check the tension. So we check for both limit states of yielding as well as rupture when it comes to tension. Then we report the compression checks. So flexural buckling about the major axis. Remember, X is the major axis in this case. So flexural buckling about major axis, flexural buckling about minor axis, flexural torsional buckling. And then it goes on to check the shear along the major axis, shear along the minor axis, and then does the bending checks. So for bending, you have the flexure about the major axis, flexure about minor axis, and then the lateral torsional buckling. And once all of these are individually checked, it goes for the interaction checks. So, and if you note all of these, for all of these checks, it's reporting the ratios, the critical ratio, and the equation numbers that it uses from the code. And at the very end, there is some detail provided for the deflection checks as well. So this is the actual deflection followed by the allowable deflection. So since we included DFF as 360, so it has divided L by 360, and that's how it arrived at the allowable value of deflection. So so these are the various checks that the software carries out, and this was a check code. But if you want to do like a member selection, then also design command is only going to be different. So instead of check code, you're going to use this set of commands. So I have basically listed this so that you can use this sequence of commands for the design. So it starts with analysis, then you ask the software to do a member selection. Then there's a grouping that is required. The grouping is necessary because the software is going to select the individual best fit section for each segment. But to get a more practicable design, you would like to have the same cross-section for your entire physical member. So that's what you achieve through the group definitions. Then you follow it up with another perform analysis. Since you are doing a member selection, your stiffness of the structure is changing. So you are analyzing the structure once again so that your member forces are are the latest, and then match your member sizes. And finally, you do a code check. Even after doing the code check, if you note that there are still some failures, you may have to repeat a couple of cycles of these commands. So one thing that we are really excited about is a generation of the general arrangement drawings. Now, from your STAAD.Pro model, you can just directly generate the GA drawings, and you can do it for both concrete and steel using something called Steel Auto Drafter. Although the name is Steel Auto Drafter, but it can generate GA drawings for concrete as well. And these drawings are completely customizable. You can generate plans and elevations. If your model has projections, then you can just generate plans on these projections as well. You can do a material takeoff and export your drawings to GXF and also to DGN and opening MicroStation. So I'm just going to go back to the model for a second, and let me turn the node numbers off. And then we just go to the Steel Auto Drafter. So this is the Steel Auto Drafter interface. The first thing you may notice, there's a little cube out here, and these little cube would allow you to change your view to some preset views pretty easily. For example, if I want to view the structure from the left, I can just click on the left face of the cube. And if I want to view the structure from the front, I can click on the front. And if you click on the corner, it goes back to the isometric. If I click on the top, it gives me a plan view. So pretty cool that you can do it this way. And also there's a home view where you can just get the isometric. And then of course you can rotate the structure as needed as well. So the first thing that you do after coming into the Steel Auto Drafter is you're going to set up your grids. So depending on your column location, the software is going to create some grids for you. Say, for example, A and B grids are already created in the X direction, but these are completely customizable. You can have your own grid name. It could be alphanumeric, and you could include any symbols also as part of it. Similarly, in the X and Z directions, so these are the two horizontal grids, and in the elevation also, you can create a number of grids. So you can just turn on whatever grids you want to include, and that will be included. And you can put your own name, let's say is. So whatever you want, you can do with these grids. So once you set up your grids, next is you can do customization to how the drawings are going to be shown. So you can set your colors for each of these individual entities, and then for the member labels, you can put in your own company standards. So whichever way you want to name your columns, it could start with a C, it could be something else. If your beams with your girders with moment connection could be GM, girders with shear connection could be GS, like that. So these are completely customizable inputs from your side, depending on your company standards. You can just set it up. You can set up the appearance of the various entities. Like you can set the text height, how the dimension lines are going to be colored. So let's say I want to color the dimension lines in yellow, and the extension line, maybe I can also choose yellow. So whatever you want to do, you can do it from here. My drawing unit is set to English. It could be metric as well if you need. And the beauty is you can actually save this setting as an ADS file. So basically, I can come here and I can export the style setting, and it would just save it as a file, as an ADS file, and I can just give it to any other colleague of mine, so that you can import this file into his Steel Auto Drafter, and that way you would not have to set this again. So once it's set for my company, I can just use it straight out of the box. So let's generate a couple of drawings here. So what I'm going to do is select the concrete beam at the bottom, and I'm going to draw a plan out here. You can set your own scale, and then you can choose whether you want the full sections or partial sections. And if you click on generate, it's going to generate a drawing. So as you can see, it's a CAD style drawing. So you have all your grids marked up, all your beam members marked up, column members marked up, and it also gives a description of those. Let's generate a drawing for a steel level. So I'm just going to draw a plan out here. Again, I'll just choose the same settings. So you have the drawing for the steel members. And if I just zoom in a little, there is a little intelligence that is built into these kind of drawings, because if you note, ES is what I have designated as the beams which have the shear connections at their ends. So you will notice that there is a little gap that the software has left at the end where it connects to the other members. So these are for the shear connections. And it reads this information based on the releases that I have provided in my analysis model, trying to indicate that it's a shear connection here. Whereas for this member, this girder, which has moment connections at its end, you'll see there is no gap. It straight away connects to the flange of the column. So these are little things that are in there. So all of the beam markings are there. And similarly, there's a schedule that is published with all the markings, all the section designations, all the cross-section types. And you also get a material takeoff for that particular level at which you are generating the drawing. So, so you can generate drawings like this. And it's not that you have to generate drawing one by one. You can just go to your drawing list. And there you can just choose your plan, and I'm going to generate, let's say, for all of the grids. So I just include it as part of the list. And once you do the drawing generation, then you'll be able to see the drawings for all of the levels at the same time. So here my grids are all not set up. So that's the reason why I'm not able to generate the drawing for all of the levels at the same time. But let's try with the section and see what happens. So I'm going to add this. So it generated two sections along the X direction, and it generated two sections along the and let's try a section for Z also. So as you can see, it generates a number of sections or a number of drawings automatically, and then all I need to do is just click on this automated generation, and it's going to generate the drawings for the various levels. But just ensure that you are setting up your grids prior to doing the drawing generation. Otherwise, it would not be able to find any grid numbers, and that's when the software would tell you that no grids are available, the message that we were getting earlier. So yeah, so this is how you can just generate the drawings for the various levels of your structure. And not only that, you can generate your material takeoff, and you can do it in a CAD style like this, where you're going to get each section type along with the length or area. If it's a plate, it would report the total weight in tons. So this is a CAD style reporting, or if you want a text style reporting, you can also get that. So this can be exported as an XML file and sent to your customers. So that's about the drawing generation. And I'm going to just go into steel connections and show you a couple of steel connections, just to show how easily you can just generate these connections out of your STAAD.Pro model using the RAM connection version 13.1 interface. So go back to this model, go to the analytical modeling. So the structure has to be analyzed first, and then you can just simply go to the connection design, and you can just choose any of these connections from here. Let's choose, say a chevron brace connection, and I'm going to choose a cassette connection for this. You choose which design code you want to design with. So AISC 36016 LRFD, and then this is a chevron brace connection. I'm going to use both the templates, and so ask the software to do a design, and it will do a design and give you a connection design up here. So first of all, it would show up show up as a row in the table on the right. So the green light basically means that the connection is passed with the ratio of 0.39, and you can double click on that and it will bring up the connection pad for you. So here you can see that it has actually designed a gusset connection with the braces, and you have the individual control over all of these entities. So in the connection pad, you can go and you can just choose, say, the lower right brace, and so that is this brace. And for example, the orientation of this brace doesn't look the right way. So what I can always do is I can choose this option, the orientation correctly for this one. And these are the individual controls that you have over each of these members. Say in this interface, if for the lower right brace, I want to change the number of bolts, I can absolutely do that. And the connection design also would be updated based on that. So right now I have a ratio of 0.39 based on all of the connections that based on all of the load cases that it has designed the connection against. But let's say if we change it to say 3 volts for this member, and also for the lower left brace, let me also change the number of volts to 3. And when I do that, my utilization ratio comes down to 0.26. So you can make dynamically, so you can modify your connections dynamically, and then you can save it. And all of these customizations are basically going to be retained in your STAAD.Pro model. So later on, if your STAAD.Pro model is reanalyzed, your forces are going to change, and then the software is going to just check the same connection with these 3 volts, but based on the new forces, and then it's going to tell you whether it's a pass or a fail. Or you can also ask it to optimize the connection, at which point it would check based on the new forces whether it requires the 3 volts or not. So, and it's not that you have to do these connections individually. You can actually just select all of the connections of similar type, and then have RAM connection design those. So, but before I show that to you, let me show you another type of connection. Let's say connection between a beam and a girder, and we are going to use let's say the smart connection, and I'm going to choose the AIS 6016 RFD, and this will be a shear end plate beam girder connection. I'm going to choose the templates and ask for a design. And so if you look at the design of any of these, you will see that the beam has automatically been coped. Like since the girder and the beam in this case was of the same depth, so it has automatically created the cope in one of the members. And then also you like instead of the 3D model, you can generate the DXF drawing for the connection as well, which can be exported as a DXF file, as you can see here. You can look at the results, which would give you the details of these calculations. So there'll be all of those geometry checks, then the design checks, and you have the clause numbers, the specific table numbers, the equation numbers, and each check is documented here. It will give you the capacity and also the demand for each of these checks, and also tell you like which of these load cases are the critical for that particular clause, for that particular check. And if you need more detailed calculation, there is a little icon in here. If you press that, it will give you the detailed formulas that it uses for these various calculations. So, so once you press that, it will just give you all the details. So if you're trying to do any kind of hand check on your connection design, that's the way to do it. Okay. So next, I'm going to, before I jump into the foundation design, I'll hand over this presentation to my colleague Vishwas, who's going to walk you through some concrete design, the advanced concrete design that we talked about. Vishwas.
So Sai has given a very good presentation on STAAD and steel structures. I'll cover the concrete part. So maybe can you Thank you. Sai, could you tell me once the screen is on?
Yeah, it is on.
So I'm Vishwas Date. I'm the principal product manager and mainly in charge of concrete design. The product called STAAD Advanced Concrete Design, which Sai mentioned before. So let's jump into a little presentation and then I'll run you through a small presentation on the software. So in a structural design office, the structural design process actually goes through a few steps. Typically, you will have some schematic stage and you will do some preliminary analysis. You may once your analysis is fairly established, you try and go for design detailing. At that stage also, you might want to change certain member sizes, certain properties, and you want to go, get back and forth. Once you're satisfied, then you actually make the calculations for design, get design reports validated. Then you provide detailed to site, and of course the quantities for execution as well as procurement. What we have is a software called STAAD Advanced Concrete Design, which actually handles all of this together post analysis. So let's see what kind of outputs are generated through this. So what we believe is the visualization is the most important tool, in any software. So if you can see on the screen, the top left, you have some graphs with red and blue lines. Those are actually the beam elevations in terms of the rebar requirements. Or the bottom left corner shows you a shear wall detail in plan, when you are in design process. This is not a drawing, this is during design process. Or on the right hand side, you can see a 3D PM curve for a column. So all of these are visualization tools available within the software, and we are going to have a sneak peek of those. So outputs that we produce, these are the outputs. So you have detailed drawings of columns. So column details covering the entire rebar arrangement, grade of concrete, levels, everything, including the individual link arrangements in the column, or detailed column elevations showing the level, showing the laps, showing the various zones of link. If you have a seismic detailing to be done, we can handle irregular shape of columns. So if you actually happen to have some columns which are irregular shape due to whatever constraints, you can put them as SD sections instead. We'll read those and we'll create reinforcement details for those columns. Or we also handle combined walls. So if typically your lift cores tend to be, C-shaped, E-shaped, those kind of things. So those walls are read together and analyzed and designed together. So we handle all of that. And also the beam details. So we look at detailed beam elevations. These are working stage drawings and not schematic drawings, including the reinforcement sections at various locations of the beam. These are all intelligently drawn. Let's go and have a look at how the column design is performed, post analysis. So once you have completed the analysis, generally you will want to verify the results. You will have some look at some bending moment diagrams, some deflection shapes, and all of that. And once you are satisfied that your analysis is more or less achieved the status you want to, you will go into column design. So you launch a product called STAAD Advanced Concrete Design Center. Once you are here, you will have to fill in some details like some project name, client, this is for your reference, and engineer's name. Select the code you want to. So in this case, we'll select ACI 318-2014. The STAAD file is already listed over here because you started from there. And then you choose the elements like, for example, columns and walls, and start the design project. Once you are on the screen, so data that it reads reads the geometry completely. It reads the forces, it reads the member sizes, and it also reads the things like connectivity releases between various beams and etc. All of those are important because those allow you to make engineering decisions. Once the data is read, what you can see, the screen is divided in two parts. On the right hand side is a graphical part, on the left hand side is tabular part. These screens are customizable again. In the graphical part, you will start noticing that we have put grids, we have put column numbers. Whereas in STAAD, what you always have is members. Here we have columns. Columns, what we do is we track in elevation. So from bottom to top, wherever the column goes, we track. And we identify column centers and put grids over there, including the grid dimensions, because our drawings are not complete without the grids. So this is where the intelligence in terms of what concrete design offers to you post-analysis starts. What you will notice is that all the grids are identified again as Sai showed you in Steel Auto Drafter. These grids are customizable. So if you want to off certain grids, you can do so. If you want to put certain grids additional, you can do so. Also, you will notice that it will read the shear walls. STAAD has a parametric surface model for shear walls. STAAD Advanced Concrete Design Center reads those, converts them into combined walls. So for example, CW1 here consists of 4 actually different walls, 1 horizontal and 3 vertical. They form a combined E shape. That's the reading part. Other part that you will notice is that we form something called as column families. So for example, column C2 consists of 4 members at 4 different levels. We identify the column verticality, one on the top of each other, and name them as C2. So unlike a STAAD where each member is a member, there is no specific meaning, physical meaning to it. We create that physical meaning because our drawing has to show the column numbers and not the member numbers. Other important fact is that we'll read how the columns travel vertically. Some columns may stop at certain levels, some columns may stop at top level. So if you see the levels, we identify the levels, main levels in the building. And you can see that at 4th floor level, some of the columns stop, and above that, a building shortens. So all of that is automatically mapped and trapped. So this is about the geometry. Once the geometry is clear to you, you have to move to specific design settings. In design settings, some specific settings like, for example, ductility. So you have a seismic detailing requirement, intermediate spatial, you create that check. You can choose to go for live load reduction in case you want to optimize your design. If you have done P delta analysis, then you don't need to consider slenderness effect. So you simply off that option. There are 2 design methods possible. The most common method is an interaction principle. So you choose that. Once the interaction principle is chosen, it will go by the Bresler's equation for design. Shear wall, you can define your own ratio in terms of what is the ratio of shear wall, and you can choose to design shear wall with boundary elements also if you want to. Once you have set the design settings, you have to now go to read the member forces and qualify them. So you basically define or read the primary load cases that have been analyzed. So you have 2 dead loads here, one which is a self-weight, other is a superimposed dead load, and others are live load, wind load, and earthquake load accordingly. Once you have selected the primary load cases, you have to get them into your design mold. So you have to select the primary load cases. Here, 2 dead loads together constitute single dead load. So we have combined them, and also the other cases come directly. Going to design combinations, there are various methods. So you could add from analysis. So if you have specified the design combinations in the analysis, you simply add from analysis. If you have templates which are either created by you or they're based on code, or we have standard templates in our software, you could use them and import them. Once these settings are done, you are ready for design. Once design is completed, what you will see is a column failure report. So in this case, between 0 to 12 feet, 4 columns have failed. Now, what do they mean by failure? So column failure can happen on multiple accounts. So there is a report called failure diagnostics. So if you go to that report, you will see that these 4 columns at these levels with their individual member numbers from the analysis is mentioned. And that failure is basically a detailing failure, which basically means that the given percentage of reinforcement and rebars don't fit my column. Now going further, typically when you issue drawings to site, you don't provide individual columns with individual sections. You tend to group the columns in design. So in plan, you will see the 4 corners columns to be similar, the 4 central columns to be of similar design, similar size, and so on and so forth. So there is a way to do it. So if you go to a report called snapshot, what it will do is it will list the columns of same size together, which go across multiple levels, and it will list you percentage reinforcement at various levels. So looking at this report, you could decide which columns to be grouped and which cannot be grouped. There is one more smarter way of doing it, which is facilitated to auto group. So in auto group, what it does is software identifies various columns that can be grouped because of the size and reinforcement being same post design. Or you could force your grouping. So if you decide that you want to force some of the groupings irrespective of the design requirements, you can do so. We'll see the effect of this grouping once it is done. What it internally does when it says group, it will basically combine the forces for all those columns for various levels, whatever they are, and create a single design. So now I am running again the process of design because I have grouped the columns. When I group, what I mean is my reinforcement that I provide has to be same for all the columns at a given level. Further, if it's a multi-story building, which is typically the case, then you don't change the column reinforcement across elevations every level. So in this case, I'm trying to group vertically the levels also. When I'm saying grouping, what I'm trying to attempt is to provide the same reinforcement detail at all those sections, whether it's a plan or an elevation of the column. So I am now creating groups of 2 levels at bottom, 2 levels at top, and then 3 and 2 again. So we have total 4 level groups. Once I have done that, the column design becomes very concise or shortened because I have clubbed the columns in plan and I have clubbed the columns in elevation. Now you will see some of the columns that had failed earlier, I have still not grouped them. But I can see that in plan they are similar and it might make sense for me to group them even though software is not suggesting because of the failure. So I can go to grouping window again, which I showed you earlier, and now I am force grouping the columns. Now this is not auto group, this is force grouped. So now the details of all those columns become a single group. Sorry, the video stopped somewhere. So now the 4 columns have been grouped, and now you will see that a design has been combined. But the sections have still failed. So there is one more way to handle the section design. What I can do, I can go to that local section and say redesign. What appears is the current column size and all the bars are shown white because there is no design sufficing. So let me try the maximum rebar, that is 10 number, and try the design. And with the 2.26% also it is showing a failure. So one more option over here is for me is to try the increasing the column size. Now of course it has an impact on analysis, but if I want to try this size and what is the percentage I get, I can do that. So I can put a new arrangement. It is giving me good arrangement, but only thing is there are 4 bars of smaller size, which is impractical to do. So let me change all those bars to 8 size. I make it 8 size and I check the design again. It passes, I accept. So now you see I have modified the column size that I had used from analysis. Now in a way it invalidates my analysis, but yes, you can handle that. So there is a report called column size changed, in which you can notice the difference between the original column size and the new column size. If you feel that the difference is not big, you might want to accept these and go ahead with the design without changing the analysis. Or in case you want to go back to analysis, you use the command called update analysis file. It will recreate a STAAD input file updating the properties of these particular columns which have been updated. So in this manner, I am completing all my column design. So now my columns are completely designed. Now I want to go to the next step of verification of calculations. So let me generate a typical calculation report for you. So I'm generating a report for this group. So when I open the calculation, it's a detailed text calculation report. You have at the top a reference to an analysis file and the location where it is saved and a time stamp of that saving. So that means you can always refer to your calculations and find the analysis file that was relevant to that calculation. Then it will list all the terms that are used in the analysis presentation of report, the clauses that are used. Then it checks the stability index. For example, as I mentioned, if you have not done the P delta analysis, then you might want to do a slenderness effect here. It will give the geometry of the specific column between the 2 levels, what is the height, what is the clear height, all of that information, critical combination that is there currently. Then it will do a check for slenderness. Then it will calculate the final design moments. Then it will check the P max, the maximum actual load check. Then it will perform the design internally. It will give you check for your Bessel's equation with principal discrete actions. Perform the shear design in both directions independently. Calculate the links. Provide special confining links calculation all in detail, including all the spacing criteria, everything. This report is like a textbook report. There is another report which is a quick short report which can be used internally in the organizations, which will give a summary of column design. It is not a very detailed report. It is very concise, and maybe it is just an internal checking by a senior for the junior's work. One more interesting thing that we provide, which I showed you earlier, is a 3D PM interaction curve. So let's say for a given column section, I want to check what is the 3D PM interaction. So I can go to that specific column. I can vertically go across the P's and check my section, or I can pass through all load combinations and see what is my interaction ratio and how it is changing across the line. So this is the horizontal section is for a given P. What you can see the capacities are across both directions. So these are the various design collection reports. Another important thing is quantities, which is often a requirement from consultant's point of view. So here it will list concrete quantities based on the various grades that are there, the rebar quantities based on given diameter, and give you some basic consumption ratios, which will tell you whether your design is optimized or you want to do further some optimization. So all of this is calculations, design, engineering part. What about the outputs? So let me show you a detailed drawing for a column. So before that, let me show you a report for a design for all combinations. So in this, we saw the detailed calculation in which only the critical combination was showed. In this case, I am showing you a report for a group of 2 columns across 2 levels. So actually, I'm designing 4 sections. So you can see here member number 2, member number 49, and so on, 4 sections. The most critical combination being highlighted with a dark blue color. So in this, all the combinations are shown with their individual forces from analysis, the effects of slenderness being added, and the final check being performed. So all of these are various calculation reports. Going further is the actual drawings now. So let me draw a detailed drawing for all columns. So this is the concise drawing for all columns with all the groups. So let me zoom into a local column, for example. So there are levels which are grouped. Some columns stopping at 4th floor level, so the upper box is empty. Some columns go through and through. There is a single individual wall and all of those details. Going to a local column, what you can see is first is the levels, between which levels this section is valid, the size of the section. Go zoom in a little, you will find the rebars are presented with specific lesions for each diameter. The column numbers which are grouped are properly mentioned. There is a mention of grade of concrete, grade of reinforcement, cover that is being used. If there is a confining zone, for special seismic drilling that is provided, and the links in those various zones. So this, in short, becomes a complete, documentation for the site to be executed. And as I mentioned, it is very automated, so there are no issues. Further, we also have reports like column elevations. Very often you need to show some typical elevations. So what you can see, the section, there are 2 different types of sections being used. Section 2.2 is at top, where my seismic moments are governing, so I have slightly more reinforcement compared to a lower section, so which is handled in the lapping at 36 feet level. And also the all sections below are typical section 1s. In this, you will find the lengths of each confining zone, the middle zones, the types of links, the cross sections being shown, the section marks, levels, everything. So this is a very detailed sample for one column, but this can be done for all columns individually. It will also show beams and everything in the column elevation. This is a detailed report for a combined wall. So you will see the end boundary zone length, the reinforcement details within the boundary zone, non-boundary zone. The junction is detailed with the maximum effect from both the directions. The reinforcement is mentioned from the left to right. So starting with the junction is a common to both the walls. So in one of the walls it is covered. In the middle wall there is only one junction, so it is not covered on both sides. And also for each individual wall, we'll show the link arrangement. So this in short is my column module. So let's go further to beam module. So something similar to this, I'll run through a beam module process. So similar to column, you start the beam module. So again, you launch advanced concrete design. Come here, you list the project, type of project and everything. In this, more importantly, you can design typical levels together. So you select the code, the file is already selected. It will give you list when you select the beam. So it will give you multiple floors that are with the beams. Now, in very often you have typical floors in the building. So say second, third, fourth levels are identical in design. So you may want to give the same design to both because it is difficult on site to differentiate every level. So when you combine, you will give the effect of two levels. Similar to columns, you have two parts of the graphical scene. On the right hand side, you see the graphical window with grids, column number exactly as what we saw in columns. In addition to that, now we have beam numbers. And you can see the beam numbers are like what we will provide in the drawings when we execute the details for the site. STAAD has members. Again, we convert those analysis members to physical members, which are beams. Moreover, we identify groups of the beams. Each beam is not designed individually. A beam is a part of a group. So for example, if I'm designing B2, right side of B1 is common to left side of B2 and the left side of B3 is common to right side of B2. So beam identifying beam groups is automated. Beam groups in both directions, even inclined beams can be handled. So for example, here, wherever I'm clipping, that beam is getting highlighted in the dark cyan color and the rest of the group is highlighted in the red color. Similar to columns, we have design settings. One of the important settings is ignore torsion. So various people have various philosophies. If you feel that values below certain can be ignored in design, you give that value to us. What we define is better consider whatever torsion is there in the analysis because the torsional design is very critical. So if you don't ignore any value, we'll consider all the torsional values. You can go for seismic detailing. So you select the ductile type frame, spatial or intermediate. In this case, let me continue with spatial. You can choose grade of concrete, grade of reinforcement, specify cover, whatever you have. There are various styles of detailing. So I am right now going with the maximum diameter in this case. You can specify various rebars that are available. You can say that my minimum rebar in the beam cannot be less than 5 number. So I choose that. There is one more setting to have outer rings and inner rings to be of separate diameters. So in case you have analysis which governs torsion, then you might want to provide the outer ring slightly bigger than the inner ring. Once these are set, similar to columns, you can set the basic load combinations and start design. I want to highlight this. So now we have considered two levels together. So B1 actually on 12 feet is represented by member number 1001 and on 24 feet it is represented by member number 1650. So I am combining the results of both these beams when I am designing B1. So that's how I'm giving the same design for both. So when I'm designing the beam B1 or so for the group, for the entire floor for that matter, each of the beam actually I'm considering two beams at a time and applying the worst of the design for a single beam. As I mentioned, similar to columns, we have basic settings. We could actually import the load cases and combinations from one file to another. So if you have set for one project, you can import in another project. You start the design process. After auto design, you will see this window. So in this window, what you will see is beam number. So group number, beam number, type of beam, whether it is seismic detailed or not, size of the beam, grade of material. And what you can see is that the bottom and top of the beam is divided in three zones: left zone, mid zone, and right zone. Similarly, for top, you have left zone, mid zone, and right zone. And similarly, for shear, you have left, mid, and right zone. So you have basically, if you imagine the beam or visualize the beam in elevation, it can be visualized in three different parts in elevation. So that's the philosophy. So what we do is how we arrive at this detailing. Now let me show that. So you go to a view called detail view. In this view, what you can see is the graphical representation of the beam actually in elevation. So you have entire groups seen together from B1 to B5. Each of these beams is divided in 13 locations. At top, for example, the red line indicates to you the rebar required at various stations. and wherever your cursor goes, the value is picked. The blue line represents my provided reinforcement, so it has to be above my required. As I mentioned, you have 3 zones, so these 3 zones are very clear by the dark vertical lines at the bottom, where I'm providing the reinforcement required. Similarly, for bottom, I have a red curve which shows my area rebar required. Now, this is area of rebars at a given location out of various combinations, and as we saw in 2 beams. Similarly, for shear stirrups, my spacing is the criteria, so my blue line is below the red line in this case, because it's not the area required, but it's more of spacing criteria. So this is a detailed view which we go through. So for each station, we actually go through design for all combinations and find out the worst area of reinforcement required at that location. And then we form the envelope of rebars and not the bending moment envelope or the torsion envelope. Because my design is governed by both together and not individually. Let's say after this process also you are not happy with certain location, certain beam rebar that you have. So you want to edit, you double click there, this small window appears in which it shows the current rebar arrangement, the current rebar required and provided together. You say instead of 2, I want to continue with 4 in both the layers at top and top. So I simply change that, and if it is correct, it will allow me to accept. Once I accept it, it will get reflected in the main schedule over here. Now, let's say I want to continue this across the beams. So what I can do, I can come here, I can copy that reinforcement and paste across the entire group. When I'm pasting at the back end in the software, I'm checking the requirement. So I am checking that against my what is required, and if it only permits that, it will change. Also notice that when I'm changing the reinforcement at bottom, I might also affect shear reinforcement. So I'll explain to you a little later why it has happened that way. This is how I can easily manage my reinforcement detailing. So you have to not depend on what software gives you. You can choose your own way of detailing. Further, similar to columns, let me go through design calculation reports. So let me select one beam which is governed by torsion. So I'll go for a beam group G6 because it has SFR or skin face side face reinforcement or skin reinforcement or what we call. So similar to columns, we have details of analysis file, where it is saved, last saved location, time and everything. It gives you a list of symbols. The symbols, some of the symbols are directly from the code. Some of the symbols we have added to explain the report in a better manner. Going down. Then we have a lot of clauses from the code which are important clauses. We have not listed all of them because sometimes that is too much, but individual important clauses have been considered. Then we have the geometry of the beam. So in this case, as I mentioned, you have 2 beams, one at 12 feet level and one at 24 feet level. And then the clear span, effective depth, all of that. Then the minimum AST required, all of that calculation. So all of those standard details are considered in the first part. Going down, as we mentioned, also we'll list the type of the beam, ductile, seismic detailing, spatial, intermediate, whatever is there. Then in the left zone, at the bottom, you can see left and mid zone, the governing section is, 12 combination. And for that combination, and at the top at the same time, you have different combinations. So you can see that governing combination between a given zone can be different depending on the bending moment diagram that happens or the envelope that gets created. As I mentioned, the reinforcement required is calculated in different parts. So one is for the flexure, pure bending moment action. Other is for torsion. So in this case, the torsion exceeds the critical torsion. So it will calculate the longitudinal reinforcement required for torsion, distribute that across the 4 faces of the beam, and then that gets added to the flexural reinforcement, and then it is provided. Now in this case, my minimum AST that is provided is sufficient for everything. So that's how we have arrived at final minimum AST. Some cases, if it's a doubly reinforced section, your compression reinforcement also may become part of, top reinforcement or a bottom reinforcement. So all of those things are considered together here. So final AST required that we saw in the graph, in the red graph, is coming out of all those 4 criteria. The minimum reinforcement that needs to be provided, the reinforcement required for torsion, reinforcement required due to cut the doubly reinforced action, and also reinforcement in case required due to spatial seismic detailing. Coming to shear design, So it will first do the basic shear design for the forces from analysis. Then it will do the hogging and sagging moment calculations for the seismic detailing, which is what I saw. So when I change the reinforcement at top and bottom section of the of the beam, it will affect my hogging capacity or sagging capacity, and will affect my sway shear calculations. So accordingly, all those things are considered together. Uh, Similar to flexural reinforcement, the final stirrups that are come out of design are also due to normal vertical shear design, torsional requirement, and special confining requirement. All the three put together will give you my shear reinforcement. The spacing criteria for stirrups are listed specifically. So some are normal basic criteria, some are based on torsion, and some are based on special seismic detailing as per the various clauses of the code. Coming to skin reinforcement or the reinforcement across the face of the beam. So based on the torsional capacity requirement, the distributed reinforcement is calculated and it has its own spacing clauses. So we consider all of that in beam design. These are my calculation reports. Now I'll go to the main part, which is the drawing. So let me consider some random sections, and I'm choosing to draw with cross section over here. So you can see it has generated automated elevations. You can save it directly from here. So any of these drawings that you see can be saved directly from here. They go into DXA format or a microsession directly, and you can save them directly there. They are completely with layers and everything. The sections we draw for the beam are intelligent sections. We move from left to right for the beams, and wherever the reinforcement changes, we draw that section. Also, you can see the zoning has been considered. So top zone, left zone, based on the reinforcement requirement and standard settings that users have created. And when we draw the sections, as I mentioned, we intelligently map the sections. So you can see some beams have 4 sections, some beams have 3, some beams have 2 sections. So this is how the intelligent detailing has been considered, for beam sections. If I go to a beam of smaller length, so you can see slightly, how the software benefits practical usage. So in this case, the length is very small. So there is no point in curtailing the top or bottom reinforcement. So we have continued the bars through and through, and we have only single section over there. Going to detailed bill of quantities. So I'll generate 3 types of bill of quantities here. So one is the summary, which we saw in column also. In the summary, we have total volume of reinforcement, total weight of reinforcement and total volume of concrete along with the ratios. Then the next type of BOQ is based on the type of the reinforcement. Also, I mentioned if you put rates, you will get the cost also. In this type, you have main links, the face reinforcement. You will see which amount is governing, and then you will get to know whether your design is in line with your understanding. And the last is for each beam, for each diameter, what is the quantity. Now these quantities are about 90 to 95% accurate. So for basic procurement scheduling or for basic planning purpose, this can be very well shared with the clients. These are 2 main modules, columns and beams. Let me just showcase few projects that for those which have been used. This is the Trump Tower. Of course, the US President Trump has invested in this real estate in India. It's in Mumbai. It's already constructed. The second is the Geo Convention Center. One of the biggest convention centers coming up in India will get operated very soon. This was one of the finalists in YI 2019 this year. This is a very multi-story tall building in Colombo. It's a 5-star hotel for ITC. And on the right-hand side, you can see a building for Mr. Mukesh Ambani, who is a millionaire, one of the biggest millionaires in India, called Residence Antilia, which is famous in Mumbai. So with that, I conclude my presentation. I thank you, heartfelt thanks to listening to me very patiently going through this. And I hand over the presentation to Sai for the further presentation on foundations. Thank you. Thank you very much.
First. Okay, so we are just going to finish off today's workshop with foundation design. So as I was telling you, STAAD Foundation Advanced is integrated with STAAD.Pro. So once you do your analysis in your STAAD.Pro, you directly can access the STAAD Foundation Advanced program from within the STAAD.Pro interface. And this is a typical kind of output from a MAT analysis. And STAAD Foundation Advanced basically has two modes of foundation design. One is the general foundation mode, which has designs for isolated footing, combined footing, pile cap, mat foundations, and also it has the plant mode, where it can design footings for vertical vessels, horizontal vessels, tank foundations, and also it can do lateral analysis of drill piles, drill piers, and analysis of vibrating machine foundations. So there's a lot it can handle, but for today's workshop, we're going to just look at some of the general foundation options and see how we can do a foundation design based on the STAAD.Pro model that we have been looking at. So let me bring up the STAAD.Pro model out here. So once my analysis is done, I'm just going to go to the foundation design accessed from the left-hand side from here. And then you can select the supports at which you need to design the foundation. You could select all supports, or you can select a few from your list of available supports. So we are going to select all supports here. And then you also get to select which load cases and combinations you want to include as part of your foundation design. So I'm going to leave out these basic cases from the start, and then include all of those serviceability and the strength cases for my foundation design, and include those, and then launch STAAD Foundation Advanced from this button. And we encourage that you do launch the STAAD Foundation Advanced always from within STAAD.Pro, because that's how the integration happens with your STAAD.Pro model. And so that way, if your analysis model changes later on, you can always just get your updated support reactions into STAAD Foundation Advanced without any extra effort. And that ensures that your foundations are always in line with your structural model. So that opened up the STAAD Foundation Advanced software. And you can see all of these foundations which are imported from my structural model. If I go to the load and factors, you will see all of those load cases from 101 to 260. What you would generally do is, once you import all of these load cases, you just need to flag these cases as serviceability or strength for the foundation design. So I'm just going to select all of these serviceability cases and then choose service as the option and do a batch apply, so that the load type for all of these are changed in one instance to the serviceability case. And then I'm going to do the same thing for the strength load cases. So select all of those and choose the load case type as ultimate and click on the batch apply. So all my loads are now properly set up. And then the real advantage of the STAAD Foundation Advanced product is it allows you to do a lot of trial and error, and allows you to come up with different types of foundation design solutions. So for example, for this project, you can start with isolated footing and see how it comes up for your project, whether it's cost effective, whether that is something you want to go with, or you can just do a foundation that's on piles, or you can do something, or you can just create a mat foundation under your structure. So all of these trials you can do in the same STAAD Foundation Advanced file. So the first one that I have defined here is a trial one, which is for an isolated footing job type. So for isolated footing, it's just some basic information that you need to input. So you have the design parameters. If you go here, there are some basic parameter inputs related to your design. So you specify unit weight of concrete, what are the minimum bar spacing, maximum bar spacing, what is the strength of steel and concrete that you're going to use, what is the minimum and maximum bar sizes for the top and bottom. So just some basic information that's going to govern your foundation design. And then you go to cover and soil, where you specify the clear covers for the foundation. And if you are using a pedestal, the clear cover for the pedestal, what's your bearing capacity, the gross bearing capacity that you want the foundation to be designed for. And then you go to footing geometry, and there are two options. One is you can ask the software to design the footing size for you, in which case you would choose the calculate dimension, and it would and you would just specify the boundaries. So you would specify the minimum length, width, and thickness, and also the maximum length, width, and thickness, and let the software choose the best fit size for your design. And you can also specify at what increment you would want the software to check the length, width, or thickness. Otherwise, if you have a fixed size of footing, you can choose the set dimension option, where you directly go in and enter the dimensions of the footing. The software just tells you whether it has passed or failed the code check. The rest is like you can also put in some factor of safety for the overturning and sliding checks and the coefficient of friction. Once you are done specifying all of these basic parameters, you just run the design, at which point of time it's going to just run through all of the load combinations that you have defined and give you a foundation design based on those. Once the design is completed, it will give you a detailed calculation sheet, and that is one thing that I really like about this software. The calculations are so detailed that if ever you want to do any hand checks, it is extremely easy. So let me actually increase the size of this window so that you can see it a bit better. So at the first, at the beginning of the calculation sheet, it gives you the footing number and the size of the footing, the length, width, and the thickness. Then it gives you the reinforcement details for each of the footings, and then it goes on to list the detailed calculation for each of the footings. So it starts with a sketch, and then goes on to give you all the details of your inputs for the design, and then the soil properties. So these are basically the inputs which are specified first, and then it goes and gives you the load combinations, the various service combinations, the strength level combinations, and then what are the applied loads that are critical for the design for each of these service and the strength load combinations. And then it goes on to give you the gross pressure at the four corners. So we input the allowable bearing capacity, the gross allowable as the 4 kips per square feet. So we just try to get as close as possible to the 4 kips per square feet. And in case there is an uplift, it also can do adjustment of pressures using a very sophisticated algorithm and give you the readjusted pressures at the different locations. And then it does the stability check. So in this table, it would report the actual factor of safety that you have against sliding and overturning for each one of the service load cases that you have defined. And then it provides the reporting for the critical load case when it comes to overturning and sliding. And after all of these, it goes into the strength checks. It does the punching shear check. As you can see, it actually draws the punching shear parameter, punching shear perimeter around your column, and then gives you the details of the calculations, and all the equation numbers in the code are mentioned along with the actual equations. It does the one-way shear check. Again, it gives you the location of the critical section for the one-way shear check, and then one-way shear check in the other direction, and then the flexure checks. So it's pretty detailed, and you can also control the level of detail by just checking or unchecking these check boxes on the right side. So that is also something that you can control. Now, if you are doing some other types of design, so let's say if you do a pile cap design, then also it's very similar. So you again basically put in some of the input parameters in here. The only thing that's different out here is you are going to specify a capacity for your piles. So as far as your lateral capacity, vertical capacity, uplift capacity, you're going to specify those values up here, and you are going to indicate the pile diameter and what's the center-to-center distance between the piles and what's the edge distance. And then you can actually put in your pile arrangement yourself in this table, or you can ask the software to find a suitable pile arrangement for you. So it will come up with a number of probable pile arrangements. So here is a 3-pile arrangement, here's a 4-pile one. If you want to go for 5 piles, that's also fine. So it will give you all of these options, and depending on which one you want to choose, you just select that and choose confirm selection. And after that, it will give you, like if you click on the show file reactions, it will give you the reactions in each of the files based on the arrangement that you have chosen and based on all of these load cases. So once you do that, then the process is very similar. You just run the design, and it's just going to go through all of these load combinations and give you a detailed calculation sheet, very similar to what we have seen for the isolated footing. As you can see here is the one-way shear check. Then again, the one-way shear check for the other direction, the punching shear check for the corner piles. So it goes into pretty detail, gives you the flexible reinforcement calculations and stuff. Let me quickly go to the third type of foundation that I have defined out here, which is a mat foundation. The only difference between the mat foundation and the isolated or the pile cap is the software follows the rigid method of design or of analysis and design for the other cases. But in this case, for the mat, it does an actual finite element analysis. So what you do is you come here, and after your supports are imported, you just define the boundary of the mat, and then you generate the mesh, and you just need to specify some basic property, like say what's the slab thickness, and then if the mat is supported on soil, you just specify the subgrade modulus of the soil up here, and just check this box, use soil spring. So pretty much this is handled exactly the way a STAAD.Pro handles it. For example, it finds out the influence area for each of the nodes in the finite element mesh, multiplies those by the subgrade modulus to give you the spring constant. And these supports are all defined as compression on the springs by default. And so if your mat is supported on piles, you can even do that. You can basically just specify your pile layout. So in this table, if I just expand this, there's a pile position table. If you have piles, you can just specify the XYZ coordinates of your piles, and then you can come here and specify the pile spring stiffness. So that also is possible. So mat supported on ground, mat supported on piles, both are possible. And once you are done with all of these inputs, you just go and then you run the analysis. And at that point of time, it basically brings up the STAAD.Pro analysis engine. So basically, there's a STAAD.Pro model that gets generated in the background when you run the mat foundation analysis, and you have access to this model in the same model folder. So it would create a folder by the name that you have given for your job, and you can actually access the .std file also. But don't modify the .std file from there. If you need to take a look at it, just copy it to a different location, because otherwise it would break the integration between the STAAD Foundation Advanced and the STAAD.Pro model. Yeah, so same detail of all of the calculations, and you can see it plots the deflected shape for this particular load case. You can also do a lot of good things, like if I go here, I can choose the soil pressure option, and it's going to show me what the soil pressure is for this particular load case. And if I select a different load case, then it will adjust the soil pressure according to whatever the current selected load case is. And then once you're done, then you go to the slab design portion, and you just input certain basic properties, like what's the grade of steel, concrete, what is the top cover, bottom cover, pedestal cover, what's the minimum bar sizes, what is the minimum and maximum spacing that you're going to allow for the foundation design. You can check this box if you want to include the wooden armor moments in the design. And once you are done, you just click on the design button, and the software is going to then give you a table, and it will give you the longitudinal reinforcement as well as the transverse reinforcement, both on the top and the bottom faces. So these are your critical moments for all of these directions and faces, and it also gives you the location, coordinate location where this moment occurs, and then which is the critical load case, and what's the reinforcement requirement in order to satisfy this moment. So these are provided in a table for you, and then After that, what you do is just tell the software what kind of reinforcement you want to go with. So you would go to reinforcement zoning. And so zoning essentially is declaring how many different variations of reinforcement you would like to have. So if I want just one variation of reinforcement, a certain diameter at a certain spacing, I would just choose one. And if I click on create zone, then it would show me, like in this diagram, that number 7 bars at 10 inch center to center should be good for this particular direction and phase. So similarly, you would generate the reinforcement zoning for each one of those phases. And another thing that I want to show you today is this moment capacity checks. Like once you do a detailed design, even before you get into the detailed design, you can actually do some little testing at your end just to see like what kind of bar diameter and bar spacing is going to work for you. For example, this is a little utility where you just provide some very basic inputs like the grade of steel, grade of concrete, what are the covers, and you specify a bar size and a fixed bar spacing. And that way, if you plot the capacity diagram, it will tell you what is the moment capacity that this particular bar size and this particular spacing is going to give you. So you now know what the capacity of the mat is at a typical cross section. And then if you plot the moment diagram, so if I go back to the plot capacity diagram, it's about 16.178 feet per feet. But if I go to the moment diagram, then you will see like the demand is about 46. So clearly the number 3 size at 12 inches is not good enough. So if you plot the failure diagram, it will show you like a significant portion of your mat is basically failing. So all the rates marked up here definitely indicate failure up here. So basically you get a sense as to what type of reinforcement can actually work, and you can also get to choose like any of the directions from here, and you get to choose the bar size and the spacing. And once you are happy with your setting, this is 46 that we already seen. But if you plot this one, the capacity diagram, now you will see that since I am using a higher bar size and a certain spacing, so my capacity is now much more. So now this should work. So if I then plot the failure diagram, it will basically show you like everything is passing, everything is in green. So yeah, these are the things that I wanted to show you in the foundation design. And also just a quick reminder that always remember to launch your STAAD foundation from within STAAD.Pro, because that is how you ensure that it's integrated. And any changes to your STAAD.Pro model would then be directly read into STAAD Foundation Advanced, because there is an import option up here in STAAD Foundation Advanced that allows you to import a STAAD.Pro model into a new STAAD Foundation Advanced file. But if you do that, there is no integration with the STAAD.Pro model. So that's the reason we suggest not using the import STAAD.Pro option, but launching the STAAD Foundation Advanced from within STAAD.Pro.